Friends, this is to introduce my book Microprocessors with a stepwise approach to advanced processors. I have a very clear objective of writing this book is that all the students of electronics and computers have to fundamentally review their digital electronics knowledge, then study the processors in a generic way, and then get into the latest processors by understanding the latest microprocessor architectures or processor architectures in mind. Okay, for that I have really gone in 3 steps. One, to introduce the complete digital hardware again, keeping in view of the processor design, and then to primitive processors in a processor agnostic way, like not going through a very specific processor, and then introducing the concepts of advanced processor architectures, and then to ARM processor. That's my objective. For that, I have introduced the number systems, again reviewing all the things what people have studied in electronics, very specific to the ones which are all used in processor design and microprocessor based programming and industrial applications. And the way the digital devices has been introduced here is to correlate the digital electronics with the computing software. I am taking as a simple example here. You will find a Z is equal to L1 is one statement, okay, where how is it in a higher language is really implemented in hardware. So I made a small display here is starting with a register where it's try to load the data, and then to a register set, then to the concept of a value which is stored. Okay, this is applied in all respects to understand the digital devices. For that, you require open processors, open collectors, tri-state bus. These are all important aspects which are needed for processor design, processor hardware, and these have been introduced. Next is starting with the computing concepts in a very generic way, then to the unforgettable 8085 primitive processor in a lighter way. The concepts have been introduced here. In afterwards, getting into the 8086 architecture in detail with the pipelining, segmentation concepts, and the architecture, which becomes the basis for assembly level programming, addressing modes, then the programming aspects, including the architectures. Once students have understood the 8086 architecture, I have introduced the application development, practical real world applications starting from a physical model. How do you get into the electrical model? Then applying a state machine to understand the real design and modeling, and then to assembly level language. Once this is done, I have introduced varieties of methods of testing, particularly logic analyzers, logic pulsars, then emulators and logic probes. These are the tests what I have introduced. Once this is done, we will go to the real processor architectures, though it is a one semester course, but we have abridged it in such a way that every student of microprocessor based design or microprocessors must learn these concepts. For that, I have introduced the memory hierarchy, cache techniques, virtual memory, all optimizations needed for at the compiler level. After introducing this, I have got into the RISC processors, today's latest processor technologies, particularly ARM, keeping it in mind varieties of mechanisms like vector architectures, SMT architectures, then to graphic processor units, then multi-thread execution. After introducing the things, I have introduced the ARM processor with all the background what they have learned in the advanced processor architectures, then ARM microcontrollers, the programming around ARM. This completes to my objective of bringing a student starting from a conceptual digital hardware design for a processor to the advanced processors which are currently being used based upon the RISC technology. Thank you all. This is my concept and this is my objective. Thanks a lot for your attention. Thank you.